All right. So the last thing we were talking about was this lovely formula. Okay? So we were talking about E equals mc squared, and how if you figure out a way to make it practical, you can make lots and lots of money and lots of interest. But how does it work in the real world? Okay, what are the applications? So yesterday, right, we were talking about it. Now, did we get to actually working with it? Were we actually doing a problem with it? No, we just introduced it right into the bell ring, right? Okay. So if we look at it, let's go through it real quick just so we can see. So if we're looking at the formula, this formula is not hard. Okay? Although people like to be freaked out by it, it's really not hard. You know what all the values mean. What's the E stand for?
Energy.
Energy. Measured in what units?
Joule.
Joules. Right? What's the M stand for?
Mass.
Measured in what units?
Kilograms.
And C squared?
Speed of light, meters per second.
Speed of light, measured in meters per second. Had a green one. Okay? Now, the first question you should have is, how is this times this going to give you that? It won't, because I haven't done it right. First of all, this is kilograms times what?
Meters per second.
What are you doing to the C? So squaring it. So not only do you square the number, but you're also going to square the unit. So you're going to end up with meters squared and seconds squared. Still, how the heck does that give you that? Well, if we look, joules, right, is a derived unit. We came up with it, right? The first time we talked about joules was using what formula? When was the first time we worked out joules?
When we did work.
When we did work. Okay? The work formula, work makes you mad, yes? Okay, what's the units for mass?
Kilogram.
What's the units for acceleration?
Meters per second squared.
What's the units for distance?
Meters.
Should these two things multiply? That ultimately gave you joules, right? Newtons times meters, or kilograms times meters per second squared times meters. Okay, so how do you get this to this?
The m times m is m squared, so it's kilograms times meters squared over second squared.
If you just break this down, you get kilograms here, leave that alone. You can break meters squared over second squared into meters per second squared. That takes care of the second squared of 1 meter. You still have that leftover meter you have to multiply by. So you get kilograms times meters over second squared times meters, gives you joules, proven by the work formula. So you know I didn't just make it up and tell you that it was just joules randomly without any sort of connection. Does that make sense? Yes? Okay. So how would we do this? How would we figure this out? Well, what we said we ultimately want to try to do is we want to try to convert mass into energy and see how much it possibly has. Yes? So let's see, how do we do that? Well, let us take the smallest possible unit of mass that I can have. Let's figure out how much energy is in one universal mass unit. take it, if we can figure out the basic, the smallest, then we can work our way up, right? Because everything is going to be some multiple of one universal mass unit. So we have a word problem like this. What do we always do first? Key. Let's make a key. Okay, what's the question asking us for?
Energy.
Energy. What letter is that?
E.
Okay, that's what we're looking for. Okay? How much energy is in one universal mass unit? So obviously we're talking about measuring what?
Mass.
Mass. What letter represents mass?
M.
So we have one universal mass unit. And when we have E and M, what's the other letter that we need to include in that formula to make it work?
C.
C. Cool? Got it? Okay, now if you just did that using the values that's here, you get 3.0 times 10 to the 8 joules, right? No, you wouldn't get 3.0 times 10 to the 8 joules. Why? What does the mass have to be here?
Kilogram.
Kilograms. What is the mass right now?
Universal mass.
Universal mass unit. So you have to convert from universal mass units to kilograms. We did this yesterday. What's one universal mass unit in kilograms? In your notes from yesterday. No. 1.66 times 10 to the negative 27 kilograms. Okay? Now you can plug that into the formula. Okay? Figure it out. Tell me what you get. Make sure your answer has the right number of significant digits. I'll do the tough part for you.
Oh, how'd you get that? I'm sorry.
I know it's so hard. Just answer the question. Use your slide rule. Go ahead. Good work. What do we got? 1.49?
494.
Well, we only have 3 digits up here, so your answer should only have 3 digits. So it should be 1.49?
1.5.
No, 1.49. Because it's 494, yes?
Oh, yeah.
Times 10 to the what?
Negative 10.
Joules. Agree? Yes? All right. Now, that's the number of joules. But here's the thing. When we talk about atoms, when we talk about particles, okay, we rarely use joules because that number is so super duper duper tiny. Okay? Usually when we're talking about energy values in atoms at the atomic level like this, what's the unit that we use? We used it when we did modern physics before.
Electron.
Electron volts. So typically a question like this would ask you how much energy is in one universal mass unit, and they'd add the extra little bonus in electron volts. So how would you convert this to electron volts? You know the conversion factor for electron volts in joules. What's the conversion factor for electron volts in joules? You don't remember it, it's on the front of your reference table. Tim?
1 electron volt is 1.6 times 10 to the negative 19 joules.
1.6 times 10 to the negative 19 joules. So what should you do with that in order to convert joules to electron volts? Multiply or divide? Divide. Okay? So divide 1.49 times 10 to the negative 10. Joules per electron volts, and joules will cancel out. And you end up with what do you get? Sophia, what do you get? 931.
2 and then 4
Well, that's a big number, right? When we have a number that's that big, you're talking the hundreds of millions, it would behoove us, it would make more sense for us to use a prefix. And so typically when you do these questions, you're going to be asked to solve the question not in regular electron volts, but in mega electron volts. Typically, these questions are going to ask you to solve for the amount of energy in mega electron volts. So what you would do is the same process that we're doing, except when you get down here, convert this into mega electron volts. Okay? How many mega electron volts is that?
1.31 times 10 to the negative 2.
Not negative 2.
That's positive 2.
Or we could just do it as 931. So we just discovered that 1 universal mass unit is equal to 931 electron volts. That number is super important. It's so important that it's on the front of your reference table. In fact, I think it's the last constant that we haven't talked about that's on the front of your reference table. Congratulations, ladies and gentlemen. You have officially completed the entire first page, second page, okay? Almost all of the third page, half the third page, and everything else. We're almost there.
Or we can do the.
Oh yeah, we will. It's not today, it's tomorrow. Okay? Does everybody understand that? Cool? At home, are we cool?
Yes.
Okay. Now, the question that everybody asks. Why am I learning this? What the heck does this have anything to do with anything that we've talked about? I'm glad you asked. Because all of this has to do with something that we started talking about yesterday. When we started talking about this, I had said that what we wanted to talk about was two types of reactions. Do you remember what those two types of reactions were? Nuclear fission and nuclear fusion. So we're going to talk about fusion.
The boring one.
Yeah. Okay, so in nuclear fusion, you take lighter nuclei usually, you smush them together, technical scientific terms, smush them together, yeah, and you make a heavier nucleus. The most common example of fusion, the most popular example of fusion that we see in the universe is hydrogen and helium. I'm obviously not doing all the numbers and coefficients and all that, but just deuterium, tritium to
DT.
yeah, to helium. Okay? Now, in this process, you take multiple hydrogen atoms and you make one single helium atom. So we're not going to get into the isotopes and the percentage of the isotopes and all that stuff. But you take multiple hydrogens, you smash them together, and you make helium. Okay? This is the process that powers the sun, pretty much. Okay? The light that you see coming through the window, wherever you happen to be right now, is produced thanks to this. Okay? Now, when you do this, you end up making a helium nucleus. Now, you guys should all remember this notation from Chem. Yes? Tim, you have to sit because the girls can't see through you. Or stand at that table behind you. Okay? You guys all remember this notation, yes? Yes? You bringing back bad memories? No?
Trauma.
Trauma? Okay. No memories? You just blocked it out? Okay.
That's good to hear.
So when you have this notation, just quickly, right? This number up here is the atomic weight. This number down here is the atomic number. Ooh, I'm gonna go find your chem teacher. Okay? So, talking about what we said today, this is effectively, right, the number of nucleons, right? And then this is the number of protons. Yes? To use the terms that we've been talking about. So if we look at a helium nucleus is going to have two protons. That takes care of the atomic number. But it's got 4 nucleons. Okay? So we've got 2 of the nucleons already. What are the other 2 nucleons? Neutrons. Okay. So there's our nucleus. Cool. So if we look at these, okay, scientists have in the lab been able to determine the mass of a proton. The mass of a proton is 1.0073 universal mass units. Okay? And then the mass of a neutron is 1.0087 universal mass units. Okay? So if we look at this nucleus, okay, we can easily figure out how heavy the nucleus is. How do we do that? Well, you can't add them straight out. What do you have to do first? Okay, multiply each one by 2, right? So you need to figure out, you know the helium nucleus has 2 neutrons, and you know the helium nucleus has 2 protons, or just keep the color scheme the same. Okay, and then you would add those 2 together. So you do 2 times 1.0073 U. Okay? You should end up with 2.046. And 2.0174, I think. Right? Yes? Both of those being U and U. I should get that rid. Okay. What do you get for a total mass?
4.0320.
4.0.
320.
320. My brain's not working today. Right? Yes? Easy, right? Cool? So that's what the helium nucleus should weigh. We ran into a problem though. If you look on the Academy of Chemistry, okay, if you look at any textbook, if you ask a chemist, the weight of helium-4, right, is not that. The actual weight is 4.0, where's the number? 0. Is that. The actual experimentally determined weight of a helium nucleus is that. Calculated weight is this. The experimental weight is that. Now, if you were in a lab and you got this, you'd give me the classic answer of human error, because that's your answer to everything. Why was this wrong? Human error, human error, human error. You think that just kind of writes things off. Okay? Except there is no error here. It's just something we're missing. Okay? This value has been determined over and over and over again by multiple scientists in multiple places using multiple techniques over multiple years, if not decades. So this is the real life. Find a helium-4 atom, its nucleus will weigh this, will have this mass. Should say will have this mass. Okay? It should have this mass. Are these two numbers the same? Okay? This is one of these things is not like the other that you used to play when you were a kid. Okay? Which one's bigger? This calculated one is bigger. Okay? So there's a missing chunk here. If we look at it, we can calculate it. We can take we can take these two masses and we can do what with them to find the missing mass? We subtract them. What do you get? I'll do the hard part.
0.0304.
Okay? This number represents missing mass, or we sometimes call it the mass deficit. Okay? It's mass that should be there that's not. Okay? Now, the second I say missing mass, your brain, little alarm should start going off in it. Because, can you have missing mass?
No.
No. The rule with mass that you did over and over and over again last year in chemistry was that mass can neither be created nor destroyed. It must be, starts with a C, ends in an unserved, conserved. Okay? So this should bother you, and it did. Yeah? It bothered the hell out of scientists. Because what scientists realized is that that mass can't just poof out of existence. Had to go somewhere. Question is, where did it go? Well, to answer that question, we got to look back at our little nucleus here. Okay? We look at our little nucleus here. This nucleus presents a problem for us. And it should present a problem to you guys looking at it. So nuclei are super small, right? You guys remember your teacher used some analogy last year. It's like the head of a pin at the 50-yard line at a football stadium, and then the nearest electron is somewhere in the parking lot, right? Just to give you an idea of how small the nucleus is compared to the rest of the thing. Some analogy in some way, shape, or form they use just so you can sort of understand what you're looking at. So right now in this picture, these two protons are super close together, and that's me drawing it on the board, right? In real life, these protons are even closer together. They're physically touching. Now that's a problem. Why? What charge does that proton have? What charge does that proton have? What should they be doing? Repelling. Why? What exists between the two of them? An electrostatic force, right? There should be a repulsive electrostatic force that pushes them apart from each other, right? Like and like repel. That's what we talked about. We saw it, right? So, and the closer the distance gets between the two objects, what happens to the force? The greater it becomes, right? Because it's an inverse relationship. The smaller the distance, the greater the force. Yes? So these guys are about as far apart from each other as you can, or as small a distance, I should say, apart from each other as you could possibly get. So the force between these two, the electrostatic force between these two, should be ridiculously strong. Yes? Based on what you know and what you have learned, should this nucleus be possible? No. This nucleus should be utterly impossible. The only nucleus technically that should be possible is what? Hydrogen. Why? There's only one proton, so there's nothing to push on anything else. So anything bigger than hydrogen, according to what we've done up to this point, should be utterly impossible. Now this is just two. You've got elements out there like uranium. Uranium's got 85 protons in it. 92, I'm sorry, 92, what was I thinking? 92 protons. Iron's got 26, right? Carbon's got 6, right? You've got these elements that have hundreds, or 100 plus, I should say, protons wedged into a tiny little space. There is no way in God's creation that you should be able to exist, but they do. We know iron exists. We can see it in the room around us. We know carbon exists. Look at the person across from you. Okay? So obviously, these elements do exist. These nuclei do exist. How is the question? How is it possible for this to exist? It's possible for this to exist because there's something else there. Inside this nucleus, there is an invisible force which acts kind of like a chain that holds the nucleus together, that keeps the protons in place. They're trying to fly away from each other, but this force is so powerful that it holds the nucleus together. It's so strong that it can resist the electrostatic force. That's why we call it the strong force. Okay? Okay? The strong force, and we talked a little bit about it way back when, right? Is one of the 4 fundamental forces in the universe. Gravity, strong force, electromagnetic force, and the weak force. Okay? It is one of the 4 fundamental forces in the universe. It has such high magnitude, because I don't want to use the word strong to talk about the strong force. It has such a high magnitude that it's actually able to conceal the electrostatic electromagnetic repulsion. It is the strongest of all the fundamentals. But with great strength, okay, comes limitations. It's super strong, but it's only super strong in distances about the size of a nucleus. Once you get to bigger than the radius of a nucleus, the strong force, its intensity drops off dramatically. So it works really, really well if you're talking about nuclei, but not if you're talking about anything bigger than that. Does that make sense? Okay? Now, cool, that's great, that's wonderful. What the hell does it have to do with what we're talking about? Well,
Radioactivity.
okay, if we're talking about a force, okay, if we're talking about force holding things together, okay, that force can't exist in a vacuum. What I mean by exist in a vacuum is something has to cause it. All forces have a cause. You can't figure out what the cause of the force is, you can't call it a force. You need to know what the agent is. Okay? And we'll finish this up in part 2 of the lesson after you take your 5-minute break.